In this problem, we're asked to find the radius of convergence of a power series. So a power series is an infinite series that also involves a variable x. And so you can think of it as a function for each different value of x. This function outputs a different value, but actually it's a little bit more complicated than that because for some values of x, the series will actually be diverging. So this function only makes sense for values of x where the series converges. And when we have a power series, one of the first things we want to do is figure out where it converges. Two related concepts are the radius of convergence and the interval of convergence. We'll find both. The primary tool for doing this is the ratio test. So we're going to take the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the nth term. If we write out what that is, we get the following expression, where the left half of this expression is the a n plus 1. I've just taken the original formula, the terms, and just replaced every n by n plus 1. And then the second half is the dividing by an. To make that look nicer, instead of dividing, we multiply by the reciprocal. So I want to simplify this, and one of the first things I'll do is take a look at the fact that I have some negative 1s to some power. But these negative 1s are inside some absolute values, so whether or not they're negative 1 or positive 1, they're just going to simplify to positive 1 once I take the absolute value. So the absolute value just kills them. Usually I wouldn't even bother writing them. Now I need to take the limit of this expression as n goes to infinity, but I do have a way of simplifying it one more step, which is that I have quantity x minus 2 to the n plus 1 divided by the same quantity to the power n. So I can subtract the powers, n plus 1 minus n just leaves a power of 1. So after canceling, we have this expression, and this x minus 2 quantity is not the variable, the x is not the variable we're calculating the limit with respect to. So with respect to this limit, the x is actually a constant. Therefore, this can be factored out in front of the limit. But when we do so, we need to be careful to remember it was inside these absolute values, and I need to keep the absolute values around them. Now I just need to calculate the limit of n over n plus 1 as n goes to infinity. You could use L'Hopital's rule if you want to be very formal, or you can just use the method of dominant terms. Either way, this is going to approach 1 as n approaches infinity. So this limit is 1. 1 times anything's just that thing, so let's get rid of the 1. We have calculated the limit, and we now have the absolute value of x minus 2. Now I want to recall what the ratio test actually says, so that we can start interpreting what this result means in this problem. The ratio test says, after we take our limit, if we get a quantity L that's less than 1, then the series converged. If we get L greater than 1, the series is diverging. And if L is equal to 1, the ratio test is inconclusive. So we know for certain that if this quantity is less than 1, this series is converging for those values of x. All right, let's try and identify what values of x actually satisfy that. So we're thinking about the values of x that satisfy the absolute value of x minus 2 is less than 1. And actually in these power series problems, you get expressions like this a lot, so I want to look at a slightly more general version of this and think about it from a geometric perspective. So the values of x that are going to satisfy absolute value of x minus a less than r looks like the following if you draw it on the number line. So it gets centered. It's an interval of values that gets centered at a and extends a distance r to the right and a distance r to the left. And in this case, we have a strict less than sign, so those two endpoints are currently not being included in my interval. In our particular problem, the value of a was 2, the value of r, which is actually the radius of convergence, is 1. So it extends 1 beyond 2, and it goes 1 to the left of 2. If all we wanted to do was find the radius of convergence, we'd be set because we already know that it's 1. But I actually want to go one step further. I want to figure out the interval of convergence. We know most of that already, but there's one thing we need to check. When L is equal to 1, the ratio test is actually inconclusive. The values where L is equal to 1 are actually these two endpoints. So these endpoints might converge or they might diverge. We don't know that from the ratio test. We're going to have to plug in those values of x back into this power series and look at them separately. So I'll start by replacing this x with, let's just say, the left value, x equals 1. So now I have in these parentheses 1 minus 2, which is just negative 1. So I have negative 1 to the n times negative 1 to the n. If n is an even integer, then these are both just 1, and 1 times 1 is 1. But also if n is odd, then these are both just negative 1, and negative 1 times negative 1 is still 1. So this always simplifies, the terms always simplify to 1 over n in this case. But this is the harmonic series, and we have shown that the harmonic series diverges. You can show that using the integral test. Another way of recognizing it is that it's a p-series where the value of p is less than or equal to 1. So we do know that the left side, it does not converge there. The power series diverges at x equals 1, so we'll leave that as an open hole to indicate that. We need to check x equals 3 separately. Replace this x with 3. Now I have 3 minus 2 in the parentheses. That's just 1, and 1 to any power is still 1. So this simplifies to the infinite series of negative 1 to the n over n. And that series actually converges. It converges by the alternating series test. It's an alternating series because it has this negative 1 to the n, so the terms keep switching between plus and minus. But also, as n goes to infinity, the terms get closer and closer to 0, and the terms are decreasing in the sequence. Like if you ignore the negative 1 to the n factor, you would have 1 over n, and 1 over n is a decreasing sequence. And those are the conditions for the alternating series test. We now know that the right side is converging. We have the full interval determined. The radius of convergence, as we mentioned before, is 1, and the interval of convergence goes from 1 exclusive, so open parentheses, all the way up to 3 inclusive, so square bracket.